In the last class, we have seen general features of the DC armature windings, and then we have just seen there are basically 5 different features of this DC armature winding. We have seen each of the features and how these have to be designed in such a way that we get maximum EMF and all those things we have seen. So okay. So let's continue today's class. And along with these 5 general features, we have already seen the definition of the commutator pitch, as well as we have seen the definition of the pole pitch. So now the next definitions which we are going to see is which we are going to see are, let us see. Okay, for today's class we'll be discussing different definitions of different terminology that are being used in armature windings, and along with those terminology, we are going to see 2 different types of windings in which the armature two different styles in which the armature winding can be wound. So that is what we are going to see in today's class. Okay. So while starting, in the first definition which we are going to see is coil span or coil pitch, which is represented by YS. Okay. It is the distance measured in terms of number of armature slots or number of armature conductors spanned by a coil. So, if you are having a coil and first side of the coil is in one slot and the second side of the coil is in another slot, the distance between these two coil sides is nothing but the coil span or coil pitch. So that is what he is explaining here. Thus, if a coil span is 9 slots, it means that one side of the coil is in slot 1, the other side is in the slot 10. So that is the coil span. Okay, that is the coil span or coil pitch, which is represented by YS. Next is full pitched coil. There are 2 terminologies in which we will be addressing these coils. Okay, these armature windings. So those are called as the full pitched coil and fractional pitched coil. Why are we calling this? What is full pitched coil and why are we calling it as full pitch? Let us see. If the coil span or coil pitch is equal to the pole pitch, it is called as the full pitched coil. You know what is pole pitch, right? Pole pitch is the distance between 2 different poles, that is the coil span, the number of slots between two what do you say, different poles, that is one north pole and another is, if one north pole is there and the other is south pole, the distance that is the armature slots between these two is nothing but the pole pitch, right? So if the coil pitch is equals to the pole pitch, then it is called as a full pitched coil. That means what exactly is this definition saying means, if exactly one coil side and the other coil side are under the influence of opposite poles, that is if one is under north pole, the other one is in the south pole, then we call that particular coil as a full pitched coil. Okay, so the coil span should be equal to the pole pitch, the coil pitch should be equal to the pole pitch. Sorry, here if you can see, one coil side is under north pole, the other coil side is under south pole. In this figure you can see here you can see one is under the north pole, one coil side, this is, let us say, coil side 1, coil side 2. So coil side 1 is under north pole, whereas the coil side 2 is under the south pole, so that the coil pitch is equal to the pole pitch. Coil pitch is equal to the pole pitch. This type of winding is called as a full pitched coil. Okay. Why are we going for this full pitched coil? Means in this case the EMFs in the coil sides are additive. That is, you can add them. Because this we have seen in case of simple loop generator, right? So if you have the EMF which is induced in one coil side will be aiding the other coil side only when those two coil sides are under opposite pole influence, right? If you have an opposite pole influence on both of the coil sides, then the EMFs generated in those coil sides will be aiding each other. So that is why we need to make sure that the coil winding which we have is a full pitched winding. So in this case, the EMFs of the coil sides are additive and have a phase difference of 0 degrees. That means there will not be any phase difference between the EMFs generated in both the coil sides. The EMFs generated in the coil sides are additive as well as they do not have any phase difference. The phase difference is 0. Okay. Next, therefore, the EMF induced in the coil is maximum. So, there is no phase difference and the EMFs induced are additive. So, what happens? The EMF that is being induced in the coil will be, the total coil will be maximum. If EMF induced in one coil side is 2.5 volts, then EMF across the coil terminals will be 2 into 2.5, that is 5 volts. They, as we are saying, those are additive, right? Therefore, coil span should always be one pole pitch unless there is a good reason for making it shorter. So, if there is no other reason, we need to make sure that the coil span or the coil pitch should be equal to pole pitch. Coil pitch should be equal to pole pitch, so that we can get the additive type of EMFs and the resultant EMF is a very higher amount than that is being generated in each of the sides. Okay. Now that is the full pitched coil. Now we are going to see fractional pitched coil. If the coil span or the coil pitch is less than the pole pitch, then it is called as the fractional pitched coil. This diagram on the right hand side is showing us fractional pitched coil. Here you can see coil pitch and the pole pitch are not equal. Coil pitch and the pole pitch are not equal. That means the coil, one of these coil side, that is the coil side 1 is under the influence of north pole, whereas the coil side 2 is not under the influence of south pole. Coil side 1 is under the influence of north pole, but the coil side 2 is not under the influence of south pole. So, this type of winding is called as the fractional pitch winding. Fractional pitch winding. Okay. In this case, the phase difference between the EMFs in the two coil sides will not be 0. So, there will be some other phase difference and will not be 0, so that the EMF of the coil will be less compared to the full pitched coil. So, EMF that is being produced in a fractional or the fractional pitched coil will be less than the EMF generated in a full pitched coil. Why is this happening? Means because of the presence of the phase difference. Fractional pitch winding requires less copper, but if the pitch is too small, an appreciable reduction in the generated EMF results. He is saying that this fractional pitch coil will require less amount of copper. Copper is nothing but the material that is being used for the windings. Okay, the windings are nothing but they are made out of copper. Okay. Now, if you can just look at these two diagrams, here the amount of metal that is required for this total connection, the amount of metal that is required for this total connection is greater than the amount of metal required for this connection. Okay. So, here the amount of metal required for this connection will be greater than the amount of metal required for this connection. So, what is happening is we are saving copper. Saving copper in case of fractional pitch winding. Okay, we are saving copper in case of fractional pitch winding. Okay, but as we go for this saving of copper, what happens is, as we go for the saving of copper, what happens is, accordingly the EMF generated will also be less. Accordingly, the EMF generated will also be less. So, how much compromise? We need to strike a balance between the saving of copper as well as the EMF less generated EMF that is being reduced. So, we need to strike a balance between these two. We need to strike a balance between these two. We need to strike a balance between these two and then understand what fractional pitch winding can be taken. That is, whether if we go for fractional pitch winding, whether that will be useful for us, or the going for full pitch winding will be useful for us. That will be decided by these factors. So we need to make sure that the EMF generated is also not less, and we are not at a loss for taking a fractional fractional pitch winding. At the same time, we need to make sure that the EMF generated is not less and the copper is also being saved. That is, the amount is also being saved. So we need to strike a balance between these two in order to decide whether which type of winding are we going for. Okay, if saving copper or if saving the economy is taking more preceding in taking more importance in that case, then in that case we'll go for the fractional pitch winding no matter what. If we do not want the EMF generated to be less, that is, if we do not want to compromise on the EMF generated, then we'll go for the EMF generated. Then we'll go for this full pitch winding and we will not worry about the cost. So we need to make sure, we need to understand whether we need more generated EMF or we can afford more cost. What is the important thing we need to decide? On based upon that decision, we either go for full picture winding or fractional order picture winding. Okay. So that is the full pitch winding and fractional pitch winding. Next topic which we are going to discuss is types of DC armature windings. From the starting, from the what do you say, construction and everything, we have been saying that there are different types of armature windings. So now we are going to see what are those different types of armature windings and what is the nature of these armature windings. Okay, the different armature coils and DC armature windings must be connected in series with each other by means of end connections, that is back connection and front connection, in a manner so that the generated voltages of the respective coils will aid each other in the production of the terminal EMF of the winding. So basically we know that there are two types of basic connections, that is the series connection as well as the parallel connection, right? Series connection will help us to increase the EMF, right? A series connection will help us to increase the EMF, whereas the parallel connection will help us to increase the current. So we in this DC winding or the armature windings, we need to make sure that these are all connected in series, and that series connection should also help the production of terminal EMF. That is, it should make sure that the EMF generated in one coil side will be aiding the EMF generated in the other coil side. So we need this is how we need to make sure our armature winding is. So there are basically two methods for making these connections, that is the end connections. Those are simplex lap winding. Second one is the simplex wave winding. So there are two types of basic connections: simplex lap winding, simplex wave winding. Okay, let us see what are these. Simplex lap winding. For a simplex lap winding, the commutator pitch is equals to 1. The commutator pitch YC should be equal to 1 and the coil span YH should be equal to pole pitch. These are the conditions for simplex lap winding. Commutator pitch YC is equals to 1 and the coil span YS is equals to pole pitch. Thus, the ends of any coil are brought out to adjacent commutator segments and the result of this method of connection is that all coils of the armature are in sequence with the last coil connected to the first coil. So I'll just show you the diagram how the lap winding is present. Here on the left hand side which you are seeing, that is figure 1.21 is the lap winding. Here one winding is connected to another one and then the end of this second winding is connected to the starting of the next winding. End of the second winding is connected to the starting of the next winding. Here you can see. Right. End starting. Sorry. Okay, this is the end of the second winding, whereas this is the starting of the next winding. Okay, this is how the lap winding connection is there. Okay, only two coils are shown for simplicity. So just to make us understand, they have only shown two coils. The name lap comes from the way in which the successive coils overlap the preceding one. Here you can see the next coil is overlapping the first coil. That's why we are calling this as the lap winding. Okay. Next is simplex wave winding. For what are the let us see what are the requirements for the simplex wave winding. So for the simplex wave winding, the commutator pitch YC is equals to 2, pole pitches is equals to 2 pole pitches. That is pole pitch into 2, pole pitch into 2, and the coil span is equals to pole pitch. So we need to make sure that our commutator pitch is equals to 2 pole pitches and coil span and the coil span is equals to 1 pole pitch. The result is that the coils under consecutive pole pairs will be joined in series, thereby adding together their EMFs. This is the right hand side 1.22. That is the wave winding. Here you can see one coil is there and the end of the first coil is connected to the second coil, but they are under one pole pitch. So they are under one pole. If you can just assume this will be north pole, this will be south pole. So these two are under south pole. These two are under south pole. And these are being connected. If you can see, this is like a wave, right? It is like something like this. The connection is something like this. So that is why this type of connection is called as a wave winding. That's why this type of connection is called as a wave winding. After passing once around the armature, the winding falls in a slot to the left or right of the starting point and thus connecting up to another circuit. So how will it end means like this. After passing through the armature, the winding falls in a slot to the left or right of the starting point and thus connecting up each connecting up another circuit. So the end of once you go always once you are going around the armature, the end of this wave will be connected to either left or right of the starting point. Like here, if you can see here, this is the starting point, right? So here is the starting point. Yes, here. Okay, sorry. Starting point. So after the in this type of connection, after everything, after going around the armature, the ending point will also be connected to the starting point. The end point will also be connected to the starting point. Thus total circuit will be completed. Continuing in this way, all conductors will be connected in a single closed winding. So like this, all the conductors will be connected in one closed winding. This winding is called as wave winding from the appearance of the end connection. Just by looking at this diagram, you can say that it is representing a wavy connection. So this type of winding is called as a simplex wave winding. Okay. And furthermore, we have some more definitions of the armature winding terminology. We are going to see them in this in the next part. So here the first definition which you are going to see is the back pitch. Let's continue. Okay, so the next definition which we are going to see is back pitch. So it is the distance measured in terms of armature conductors between two sides of a coil at the back of the armature. So here you can see what he means. This this one here you can see, if you are if you are taking the two sides of the coil, but you are measuring the two sides of the coil from the back side. Okay, here you can see from the back side, if you are measuring the armature slots or the distance between two coil sides, then that measurement is called as the back pitch. It is denoted by YB. For example, if a coil is formed by connecting conductor 1, that is upper conductor in a slot, to conductor 12, that is bottom conductor in another slot at the back of the armature, then the back pitch is equals to YB is equals to 12 minus 1, that is 11 conductors. So the back pitch is nothing but denoted this that will be denoted by the armature conductors between two sides of the coil at the back of the armature. Okay, so here you can see, here he is giving us an example. If we are connecting a conductor in one conductor 1, that is the upper conductor in a slot, and conductor 12, that is the bottom conductor in another slot, then the back at the back of the armature, then the back pitch is equals to 12 minus 1, that is 11 conductors. That is the back pitch. Okay, here you can see, in case of a lap winding, he is showing us the back pitch, as well as in case of a wave winding, he is showing us the back pitch. Okay. Next is similar to the back pitch. The next definition is the front pitch. It is the distance measured in terms of armature conductors between the coil sides attached to any one of the armature segment. So here you can see, it is the distance measured in terms of armature conductors between the coil sides attached to any one of the commutator segments. You can see here in this diagram, he is showing us the front pitch. Also, YF front pitch is denoted by the YF, and you can see the front pitch also in this diagram. Okay, so He is giving us an example. For example, if the coil side 12 and the coil side 3 are connected to the same commutator segment, then the front pitch is YF. That is YF is equals to 12 minus 3, that is 9 conductors. So he is saying that if two of the coil sides are connected to one commutator segment, then the distance between those two coil sides is nothing but the front pitch. Here you can see. In this diagram you can see here this this coil side is this coil side 1, which I'm labeling as coil side 1, and as well as this coil side which I'm going to label as coil side 2. These two are connected to one commutator segment, this commutator segment, right? This commutator segment. So these two are connected to this commutator segment, and now the distance between these two will be taken as the front pitch. The distance between these two coil sides will be taken as the front pitch. Similar to that in case of wave winding also. Here if you can see, in the same manner we can label this one as coil side 1, and we can label this one as coil side 2, and those two are being connected to a single commutator segment. Those two are being connected to a single commutator segment. So the distance between these two coil sides is taken as the front pitch. The distance between these two coil sides is taken as the front pitch. Okay. Now, the next term is resultant pitch. It is the distance. It is the distance between the beginning of one coil and the beginning of the next coil to which it is connected. So he is saying it is the distance between the beginning of one coil and the beginning of the next coil to which it is connected. Sorry. So here you can see this is the starting. This is the starting of one coil. Starting of the coil 1. Which one? This one. This one. And again similarly, this is the starting of coil 2. Okay. So we need to make sure, we need to understand that both these coils, this is the starting of the second coil and this is the starting of the first coil. So he is saying the distance between the starting of the first coil and the starting of the second coil to which it is connected. So this first coil is connected to the second coil and this is the starting of the second coil. So the distance between these two is the resultant pitch. So the distance between these two is the resultant pitch. Let us see in case of this one. Here you can understand much more clearly. Here this is a starting point. This is a starting point. Starting of coil 1. Similarly, here you can see this is the starting of coil 2. So so we have these two, and now the distance between these two. So and now the distance between these two is taken as the resultant pitch. The starting of the first coil and the starting of the second coil, and The distance between these two is taken as the resultant pitch. So that is the definition of the resultant pitch. So let us see. Okay, it is denoted by YR, that is what I am saying. Therefore, the resultant pitch is the algebraic sum of the back and the front pitches. So here we can just say that the resultant pitch is nothing but the algebraic sum of the back and front pitches. Next is the commutator pitch. Next is the commutator pitch. It is the number of commutator segments spanned by each coil of the armature winding. Commutator pitch is the number of commutator segments spanned by each coil of the armature winding. So how many commutator segments are there in a coil winding, in a winding? That is what is the commutator pitch. So for lap winding, the commutator pitch is equals to 1, just 1. How is that? Let us see. We are taking lap winding, one of first coil side and the second coil side of one coil. The first coil side and the second coil side of one coil are just connected to the adjacent commutator segments. So we will have only one. Here he is showing, right? Sorry. Here itself is showing YC. That is, we are having only one segment. We are only having one segment as the difference between these two. So YC is equal to, that is the commutator pitch for lap winding is 1. Okay, is 1. Whereas while coming to the wave winding, here you can see what starting of this coil side, the connection is there here, and the ending of this coil side is connected here. So this segment and this segment. So the distance between these two commutator segments is the commutator pitch. With the distance between these two segments is nothing but 2 into pole pitches, 2 pole pitches. So the commutator pitch for wave winding is 2 pole pitches, whereas the commutator pitch for simplex lap winding is YC is equals to 1. Okay. Next definition which we are going to see is progressive winding. Progressive winding. A progressive winding is one in which as one traces through the winding, the connections of the commutator will progress around the machine in the direction as is being traced along the path of each individual coil. So progressive winding. In progressive winding, what happens is as you go on tracing the coils, the commutator segments which are connected to the coils will be around the commutator. Okay, around the commutator. I'll show you like this. Now the progressive winding is the front connections, all these connections, as we go on, the connections will be, the commutator segments and the connections will be moving forward. That is why we are calling it as the progressive winding. So here is saying YB is greater than YF, that is back pitch will be greater than front pitch in the case of progressive winding, and the commutator pitch will be +1. The commutator pitch will be +1. So in case of progressive winding, the back pitch will be greater than the front pitch, as well as the commutator pitch will be 1. There is another type of winding called as a retrogressive winding. A retrogressive winding is one in which as one traces through the winding, the connections to the commutator will progress around the machine in the opposite direction to which they are being traced along the path of each individual coil. So what happens here is, if you are just trying to trying to move from one conductor to another conductor, that is from one coil to another coil, the commutator connections will be moving in the opposite direction. In case of progressive windings, the commutator along with the winding direction in which the winding is being taken traced, the commutator segment numbers will also be in the same direction. It will also be proceeding in the same direction. Whereas in case of retrogressive winding, as you go on from one coil to another coil, the commutator connections will be moving in the opposite direction. Then it is called as a retrogressive winding. Okay. Here, okay, here in case of this retrogressive winding, the front pitch will be greater than the back pitch, whereas in case of what do you say, progressive windings, the back pitch is greater than the front pitch, but in case of retrogressive winding, the front pitch will be greater than the back pitch, and the commutator pitch will be -1. The commutator pitch will be -1. A retrogressive winding is seldom used because it requires more copper. So this type of connection you won't be seeing very much. This is very rarely used because the amount of copper required for this type of winding is greater than the progressive windings. So we'll always go for the progressive windings rather than the retrogressive windings. So the next small topic which we have is the general rules for the DC armature winding. So we have seen general features of the DC armature winding, and now we are going to see general rules for the DC armature winding. So what are the general rules means? The back pitch as well as the front pitch should be nearly equal to pole pitch. We need to make sure that the back pitch as well as the front pitch should be equal to pole pitch. This will result in increased EMF in the coils. If we do that, then the amount of EMF will be increased in the coils. Both pitches, that is the front pitch and the back pitch, should be odd. So they should be odd numbers. Okay. This will permit all end connections, that in brackets as well back as well as front connections, between a conductor at the top of the slot and one at the bottom of the slot. So if you are maintaining the back pitch and the front pitch as odd numbers, then all the conductors can be connected in both front as well as back connections. Otherwise, the conductors might not be connected in front or back connections. Okay. The number of commutator segments is equal to the number of slots or coils, or half the number of conductors. That is, conductors is nothing but the coils and all. Okay. So the number of commutator segments is equals to number of slots, that is equals to number of coils. We should maintain this ratio. It is because each coil has two coil ends and two coil connections are joined at each commutator segment. That is what he's saying. This also we have discussed this. Right? The winding must close upon itself. That is, it should be a closed circuit winding. This also we know. These are the general rules of the DC armature windings. Okay. Okay, let's stop here for today.